Now let's look at inference in Bayesian network, particularly exact inference. We're going to see that unfortunately exact inference is not that economical as compared to the representation itself. So the task for any probabilistic inference is to compute the posterior probability distribution for a set of query variables. That's the unconditional probability distribution for a set of query variables given some observed event. Okay, that is to be able to assign values to a set of variables based on this observed event. Now, using the notation that we already introduced in the last lecture, we will take X to denote the query variable, E to denote the set of evidence variables, and small e to represent a particular observed event, and Y to denote the non-evidence and non-query variables, otherwise known as the hidden variables. So based on these notations, we can see that the complete set of variables are basically going to be the union of the query variables, the evidence variables, and the hidden variables. If you take them all together, you will have the full set of random variables. And a typical query will ask for the posterior probability distribution. Okay, so what is the probability of the query variable given the observed event, or given the observed values of the evidence variables E? This is what we would like to be able to answer. Now, in the burglary network example, we will want, for example, to be able to answer what is the probability of burglary occurring given that John calls and also Mary calls. Okay, so you can see the query variable is burglary. The evidence variables are John calls and Mary calls. The hidden variable in this case is the alarm. The alarm sounded. Okay, so that will be our Y. We're going to see how this is done, but I'm showing you the answer here. We will see how these values are computed. So the probability of burglary occurring based on these two calls, Mary calls and John calls, is 0.284, and the probability of not occurring is 0.716. Okay, let us see how we do that. And we're going to do that using what is called inference by enumeration. Now, in the last lecture, we saw that any conditional probability can be computed by summing terms from the full joint distribution. So we're going to try and do the same, but based on our Bayesian network. Okay. More specifically, we saw that a query P of X given E can be answered using this formula. So P of X given E is the same as alpha times P of X and E. Okay, where alpha is a normalization constant. And we saw that the probability of X and E can be computed simply by marginalizing the hidden variables. So Y is the hidden variable. Just sum across all possible values of Y and you will be able to obtain this probability. So how does this, let's call this equation 2 and try to see how this will now apply this general notion that we learned from the last lecture. How does it apply to our Bayesian network? Okay, so it's the equation 1 shows that the terms, the equation 1 here means the semantics of Bayesian network, which we saw earlier. Now equation 1 shows that the term P of x e y can be written as product of conditional probabilities from the network. Therefore, the query can be answered by using a Bayesian network by computing some of the products of conditional probabilities. So consider this query. What is the probability of burglary occurring given that John calls is true and Mary calls is true? Now, here we have to try and identify what is the query variable, what are the evidence variables, and what are the hidden variables. Once you are able to identify those, then we will be able to use equation 2 to answer this query. Okay, so obviously the query variable is burglary. The evidence variables are John calls and Mary calls. And therefore the hidden variables, which we don't know, are earthquake occurs and alarm sounded. So those are hidden variables. And therefore, so the hidden variable are earthquake and alarm. And therefore, from this equation 2, we can say that the probability of B given JM, so again here I'm using abbreviation, B for burglary, J, we have to use a small term since this is now a value. So J means John calls is true, and M means Mary calls is true. So this is the same as, based on equation 2, alpha times B of alpha times probability of BJM. And this, according to equation 2, is alpha times the marginal probability of all the 5s BJMEA, but marginalizing over A and then marginalizing again over E. Okay, so this is basically the formula. Now the semantic of Bayesian networks, equation 1, already gave us the meaning of P of BJMEA. Basically, we just need to multiply the product of each of these probabilities given its parent. This is what equation 1 says. Okay. Now, for simplicity, we will just show how this can be done with probability of burglary equal to true. Once we see that, we can do the same for probability of burglary equal to false, given the other two variables. So if you just take the B equal to true, this formula is equal to probability of B given its parent. Well, B has no parent, so it's just probability of B. Probability of E also has no parent, so just P of E. But probability of A will be a conditional probability given its parent B and E. Okay, probability of the alarm given probability of B meaning burglary occurred, and E means earthquake occurred. And similarly, the probability of J will be a conditional probability given that of the parent. So P of J given A, and finally for the M calls, it's going to be P of M given A. So this is what we obtain directly from the definition of this conditional probability. So all we now have to do is read up these values from the table and try to summarize them. So to compute this expression, we have to add 4 terms, each computed by multiplying 5 different numbers. Okay, 4 terms in the sense that there are 2 different values for A, whether the alarm sounded and whether it doesn't sound, and whether the earthquake occurred or it doesn't occur. So those gives us 4 different terms. Each of these involve 5 different values. So we have to read up these values from the table and multiply them up. In the worst case, the complexity of the algorithm for a network of n Boolean variables can be as much as big O of n times 2 to the power n. So you can clearly see that this is really going to be very expensive. In this case, we may be able to improve by factoring out probability of B, because actually probability of B is going to be constant. So you can factor it out to make the expression a little more easier to compute. You may be able to have something like this. Okay. Yeah, and similarly, once you the probability of E can also be factored in the other term. So this is the simplest expression you can have, but still it's going to be very expensive. As you're going to see in the next slide, how we actually compute these values. These are the ways we have to compute the values. Okay, for the 4 different possibilities. Just reading them off from the table. You can in fact see that there is even repetition here. This is the same as this, and this is the same as this. Yeah, so this is really very expensive. The final value you're going to get is something like this. For the probability of burglary occurring is going to be this. After you multiply all of this, and then add to get a value, multiply with this to get another value, and then do the same with the other side of the tree, and then finally multiply with this, you will have this value. Okay, now you have to do the same thing for the not B, probability of not burglary occurring. So you're going to have another similar tree like this, and with these 2 values, now you can normalize because they must add up to 1. So you add them and divide by the sum, and you will be able to get this. So this is how you may be able to compute this probability. So you can see that although it can be done, it is really very expensive. Now there are methods to improve on this. There's, for example, what is called inference by variable elimination. I will not be going into that in this lecture, but it is possible. So this exact inference can be improved, but the bottom line remains the same. So the bottom line is exact inference, even in Bayesian network, is an intractable problem as the number of variables grow. It's a very expensive process. There are ways to improve it, but it is still very expensive. But the good news is, in many AI cases, we don't really need exact probabilities. We can get away with an approximate probability. okay, that will do just as well. And therefore, the last topic we're going to learn in this lecture is approximate inference. Is there a way we can do inference to get approximate values that is much faster than the usual exact inference? And the answer is yes, there are ways. So approximate inference then, say given the intractability of exact inference in large multiply connected networks, it is essential to consider approximate inference methods. Randomized sampling algorithms, also called Monte Carlo algorithms, provide approximate answers whose accuracy depends on the number of samples generated. Okay, so what is done here is some samples, many samples actually, are generated automatically based on the conditional probabilities, and then we generate an inference by simply looking at the values in those samples, as we shall see. So we're going to consider two of these algorithms, random sampling, also called rejection sampling, and likelihood weighting. So we'll look at these two algorithms briefly. So consider the following example of a Bayesian network. So we're going to consider a different example, not the alarm example again, but a slightly different example. So here again we have a Bayesian network, this time consisting of 4 nodes. So the idea basically of this example is that someone is trying to travel by train to another place so that he can attend some meeting. Okay, and we want to be able to compute the probability of him attending that meeting or missing that meeting. And there are many factors to look at. In this particular network, we concentrate on 4 different factors. He's going to travel by train, so him being able to meet his appointment depends on whether the train is delayed or it came on time. If the train arrives on time, most likely he will be able to attend his appointment. But if the train is delayed for some reason, then he may miss his appointment. Okay, this is one. Now, what about the train being on time or being delayed? So here there are 2 factors. The train may be delayed because there may be maintenance on the rail track. On the track of the train, there may be maintenance. If there is some maintenance on the rail, then the train may be delayed. Similarly, if there is rain, especially if it is a heavy rain, then again the train may be delayed. So there are 2 possibilities, or there are 2 parents, if you like, for the node train in this Bayesian network. Okay. Similarly, maintenance on the rail may be possible if, for example, there is no rain. But if there is heavy rain, most likely the maintenance will not take place. So maintenance is dependent on the rain. How is the situation of the rain, whether there is heavy rain or light rain or no rain at all. So this is basically the network we are going to consider for this example, and to be able to explain approximate inference using it. Okay, these are the probability distribution, conditional probability distribution for the different variables. Obviously, for the rain is unconditional probability. So 0.7 for none, most of the time it doesn't rain. 0.2 for light rain, and 0.1 for heavy rain. For the maintenance, as we said, it depends on whether there is rain or no rain. So if there is no rain at all, the probability of maintenance is 0.4, and the probability of no maintenance is 0.6. The probability of maintenance is 0.2 if there is light rain, and 0.1 if there is heavy rain. So as you may notice here, we are showing even the probability of the no maintenance, even though this can actually be driven from the first column here. Okay, but just to observe, comparing with the last example. What about the train? The train arriving on time or delayed. Okay, so here, because there are two parents and one of the parent has 3 variables and the other parent has 2 variables, we're going to have 2 to the power 3 possibilities, which are 8 possibilities, as you can see. None, meaning no rain, and then there was a there was a maintenance, no maintenance. And similarly for the light rain, yes, there was maintenance, no, there was no maintenance. And the last one, heavy rain, yes, there was maintenance, no, there was no maintenance. These are the possible values. So again, we are adding the other value anyway, although you can derive it from the first column here. The last conditional distribution is about the appointment itself, whether we were able to meet it or miss it. So this depends only on the train, and therefore we have 2 possibilities. Okay, on time, so if the train is on time, the probability of attending is very high, 0.9. But if the train is delayed, the probability of attending the appointment is 0.6. All right, so the opposite probability, just subtract from 1, you will get those. So really there's no need to save this one, but just for more detail. Okay. So let us see how we can do approximate inference using sampling. So sampling involves taking a sample of all the variables inside of a Bayesian network. This means taking one of the values from each node according to their probability distribution. Just sample and pick one value. So starting from the root node, rain, we pick one of its values according to its probability. Okay, as we saw there in the last slide, none has probability of 0.7, light has probability of 0.2, and heavy has probability of 0.1. So we're going to try and pick one of these values based on these probabilities. Not just, we don't pick them equally likely. We try to pick one of these values randomly, but based on their probability distribution. So suppose in this first sample, we pick none. Then we go ahead and do the same thing for the maintenance. Pick yes or no, depending on the probabilities. Okay, so again, suppose we pick maintenance to be yes. And then we again randomly pick one of the values for the train, whether it is on time or it is delayed. Again, based on the different probabilities that we saw there in the probability distribution table. And finally, we pick one of these randomly according to the probability. So let us say again we pick attend. Okay, so this is one sample. Picking a value for each of the random variables according to their probability distribution. Then we pick another sample. Okay, so sampling is done for hundreds or thousands of times to generate as many samples as possible. This is basically how these algorithms work. So suppose we pick these 8 different samples. Okay. Now, based on these samples, we should be able to answer queries. For example, suppose we have the following query. What is the probability that the train is on time? What is the probability that the train is on time? So to do this, instead of going by the formula of calculating the exact inference, we just go through our samples and see out of the samples we have, how many of them do we have this fact being true, that the train is on time. Okay, now these are the 8 samples again. If you look, 6 of them, the train is on time. So on time, on time, on time, on time, on time. Only 2 of them, the train happened to be delayed. And therefore, we can easily answer this query, which is actually an unconditional probability. Just what is the probability that the train is on time? Well, the train is on time, according to our sample, occurs 6/8 times. 6 out of 8 possibilities. Okay, that is as easy as that. This is basically what the sampling does. So obviously you're not going to get the same answer each time, but with big sample of thousands or thousands, the likelihood is that you will always get something close, something similar. Okay, it's just approximate, it's not exact inference. So something reasonable will usually be obtained if you have a large sample. Let's take another example on the same sample. What is the probability of light rain given that the train is on time? It's a posterior probability. What is the probability of rain being light? So there's a light rain given that the train is on time. So again, we follow the same process, but there is a slight difference here. We don't consider all the samples. We consider only those samples for which the train is on time. Okay, and then count those for which the rain was light, or for which there was light rain. Okay, so if you look at the samples again, we're not going to count these 2 because for this they didn't meet the condition. The train was delayed here. The train was delayed here, so we don't count these ones. We only consider the other 6 where the train was on time. And from among those, how many do we have rain equal to light? So again, we have only 2. Rain equal to light here, and rain equal to light here. The others were none, heavy, none. This is not counted, sorry. Yeah. So this is these are the 2 cases where our condition is met, and therefore we can say this probability is 2/6. Okay. So this is the idea. You can see that random sampling, once you are able to generate your sample, the answer really is very easy. Just counting those samples that meet your condition. Okay, so this is one example. This sampling actually is also sometimes called rejection sampling. Why? Because you can see some of the samples are rejected because they didn't meet the condition here. Okay, so this algorithm is called rejection sampling because some of the samples may be rejected. And that takes us to the next type of sampling, which may be better than this one in some cases. So the sampling procedure we just used in the last example is called rejection sampling, because of course we are rejecting some of the samples that didn't meet our condition. Now, one problem with this rejection sampling is that if the evidence that you are looking for is fairly unlikely, then you will be rejecting a lot of samples. And you can imagine that it takes some computational effort to generate those samples. So if you generate 1,000 samples, and it turns out that 900 of them are going to be rejected, then there is a lot of waste of time and resources and effort. And in that case, therefore, the rejection sampling may not be appropriate to use. Okay, so we have another type of sampling which is called likelihood weighting. Likelihood weighting. Let us see how that works. So in likelihood weighting, the goal is to avoid throwing out samples that didn't match the evidence. And therefore, here is what you do. Before you start taking your sample, you actually fix the values for the evidence variables. All right, so you say if you are looking for only cases where the train was on time, you will say, okay, we will fix the value for train on time to be true for all the samples, and then try to generate the samples for the non-evidence variables. So sample the non-evidence variables using conditional probabilities in the Bayesian network, as we have done before. And also weight each sample by its likelihood, the probability of all the evidence. Yeah, this is the additional thing that we have to do. We have to level each sample by its likelihood. This is why it is called likelihood weighting. So if we repeat the same query as before, what is the probability of light train given that the train is on time? In the case of likelihood weighting, we're going to fix this variable. Train on time is not going to change. We will just sample the rain. Okay, so suppose we pick this time light rain, and then we sample the maintenance. So suppose we choose maintenance to be yes. For the train on time, we don't change it, so we pick, this has been fixed, so there's nothing to pick here actually. For the train being on time or delayed, we don't sample it. We're going to fix this to be the same. And finally, we pick the a value or a sample for the appointment. So suppose we choose attend. Okay. So once we have this sample, we're gonna evaluate it based on its likelihood and label it accordingly, and then generate another sample. So we generate samples like this, as many as possible, and based on the sample, then we will be able to answer the query. This is basically the idea of likelihood sampling. So in summary, in this lecture, we have learned that a Bayesian network is a directed acyclic graph whose nodes correspond to random variables. Each node has a conditional distribution given its parent, except the root nodes, of course. And that Bayesian networks provide a concise way to represent conditional independence relationship in the particular domain. And that Bayesian network specifies a full joint distribution, of course, in a much more concise manner. Each joint entry is defined as the product of the corresponding entries in the local conditional distribution. A Bayesian network is often exponentially smaller than the normal explicit joint distribution, as we saw in our examples. And then we saw that exact inference in Bayesian networks can still be very expensive, especially as the number of variables increase. And then finally we saw two examples of approximate inference where we can still do inference without the cost of the exact sampling, and where the answer may still be reasonable. And the good news is that in AI, in most cases, we are not really looking for the exact probability. So random sampling or approximate inference is a very common thing actually in AI. This brings us to the end of this lecture. Thank you very much.